We'll go back to that.
Would you think, well, when would you think that sort of the recognition of the usage, usefulness of
sometime in the 21st century? I don't know when. It's hard to make a prediction.
I see, and also, well, there is an argument also in Japan that the so-called nuclear fuel recycling system is not necessary to have, because we have so much abundant, well, unuseful plutonium available, and we have to rather, well, think of getting rid of that those well, excessive plutonium.
Yes, well, we have, of course, tons, 50, 100 tons of plutonium, weapons-grade plutonium in the United States and Russia, and I believe and we need to get rid of that now, and I believe the way to do that is through burning it in reactors, the so-called MOX approach, mixed oxide fuels, uranium and plutonium, and I believe that's the only way that we can really get rid of it, and the only way, by the way, that the Russians will accept. In other words, if we just bury the weapons-grade plutonium, the Russians will say, we remembered where we buried it, you see, so we could go back and get it. And the only way is to sort of render it relatively unsuitable. It's not completely unsuitable, but relatively unsuitable for nuclear weapons by burning it and producing electricity and reducing it to a form that has a much lower concentration of plutonium-239 and a higher concentration of plutonium-240, which makes it relatively unsuitable for use as the explosive ingredient of an atomic bomb.
Mm-hmm. And would you think that the U.S. government is now taking seriously your advice and recommendations?
Yes, I don't. I think it's the advice and recommendations of many others as well. But that seems to be the present position of the United States government.
And with those methods of burning up excessive plutonium mixed with the uranium, doesn't it mean that the nuclear fuel recycling systems introduction can be postponed indefinitely in the future?
Well, it isn't that large an amount. I mean, from the standpoint of the requirements for electricity in the United States and Russia and throughout the world, it's not that large of the total proportion of electricity that can be produced that way. So I don't think it'll have too much an impact on the question of recycling.
So then, in your view, sooner or later we have to think once again seriously about the making that the recycling system possible.
I do, yes. I think so. And a number of countries are doing that.
Then what can you advise to the Japanese people who are involved in that the project and who have now lots of problems and the troubles?
Oh, I would advise them to stick with it. I think they're on the right track.
But in case of Japan, the accident of Monju was caused by somewhat predicted nature. That is the handling of the metal and the cooler, because it is so explosive and so forth. Isn't that the fact that the system and structure itself is quite vulnerable, even though that the fast breeder reactor is quite useful in theory, but in practice it is very difficult to handle it?
Oh no, I think those problems can be overcome, and shouldn't stop the development because of one incident like that. And we can have containment structures around the reactor so that if there is an accident, it wouldn't result in anybody being hurt. We had the 3 Mile Island, of course it wasn't a breeder, but a regular reactor accident in the United States, but it had containment. It was a complete meltdown, and due to the containment, nobody was hurt. No, not a single casualty. So it can be handled.
I see.
The other methods of developing electricity have a much more adverse effect on the health and casualties and deaths and so forth. The coal mining leads to black lung disease, where you have tremendous numbers of miners, tens of thousands of miners, premature death, and then you have the air pollution from burning fossil fuels, acid rain, and then the possibility of the greenhouse effect, which will affect the whole world. So the use of fossil fuel is more of a health hazard in the long run than the use of nuclear power, by far.
So you think that the liquid sodium can be handled by the human beings safely and
yes,
controllably?
I think it'll be possible to handle liquid sodium and overcome these problems.
今年85歳のシーボーグ博士は1912年アメリカ中西部のミシガン州でスウェーデン系の両親のもとで生まれ、少年時代に一家がカリフォルニア州に移り住んで以来、今もここサンフランシスコ近くの閑静な住宅街に居を構えて毎日元気に大学に通っています。プルトニウム発見で有名なシーボーグ博士ですが、1930年代の後半、放射性同位元素を医療に用いる研究がようやく始まった頃に、コバルト60ですとかヨード131といった今でも世界中の病院で広く使われているアイソトープを次々と発見したことで、医学界からも高い評価を受けています。自分で働いた金を貯めて大学に進んだというシーボーグ博士、その自分自身が発見した放射性同位元素が母親の病気の治療に役立ったこと、そしてその母親の生まれ故郷であるスウェーデンからノーベル化学賞を受けたことは、長い人生の中でもことのほか嬉しい出来事だったようです。
And this is a picture taken with my mother and my younger sister, Jeanette, in front of the house where I was born.
You were born in Swedish-American family?
Yes. I was born of a mother that was born in Sweden and a father whose parents were both born in Sweden. I finished school in the Los Angeles School District. Actually, I went to high school in Watts, which was sort of the Harlem of Los Angeles. Mm-hmm. Well, I had a high school teacher who just preached the subject. He just made us sit on the edge of our seats. He told us about the discoveries that were being made, that the controversies that were raging in the, among scientists as to which theory was correct and so forth. And I just more or less said, why hadn't anybody told me about this? I just thought this was the best thing that had ever happened to me, and I decided to become a scientist. I went to school there 4 years, and then I went to UCLA, and I got a degree in chemistry at UCLA, and then I went to Berkeley for my graduate work. I finished UCLA in 1934 and then went to the University of California at Berkeley for my graduate work, where I got my PhD in 1937, doing research work in nuclear physics.
Yes. At that time, when you went into Berkeley, Berkeley was a kind of a mecca, and in your book, in your own word, glamorous atmosphere of the flourishing development of the nuclear chemistry there.
Yeah, when I started graduate school at Berkeley in 1934, it was just sort of a magic land. I mean, a mecca, just an amazing place with all the professors that I'd heard about at UCLA who had written our textbooks. There was, of course, the famous Gilbert Newton Lewis, the famous, perhaps the world's most famous physical chemist. And then there was Ernest and the cyclotron, and Robert Oppenheimer, the theoretical physicist, and many others. So when I came to Berkeley, I was just sort of walking in air. I couldn't believe it. The authors of the textbooks, practically all of them that we'd used at UCLA, were there at Berkeley. They were actual people. They were walking around. And all of those people that I had, come to revere, to just look up to, here they were, right at Berkeley, and they were actual people.
That sort of atmosphere and also the method of, let's say, giving higher education really helped you to develop your specialty on...
Oh, yes. This really laid the background, and then for me. And furthermore, when I obtained my PhD in 1937, my first job was to serve for 2 years as the personal research assistant to Gilbert Newton Lewis. Well, you can imagine that really built up my confidence. I mean, I figured if I could hold my own with the best chemist in the world, maybe I'd do all right. While I was working with him, during the evenings and on the weekends, I was working identifying isotopes produced at the cyclotron.
Yes.
And he knew that. And that's when we found those isotopes, technetium-99m and iodine-131 and cobalt-60 and so forth,
yes,
that are the workhorses of nuclear medicine today.
That is something I'd like to ask you now about the radioisotopes. You discovered not only plutoniums and all those transuranium elements, but also many isotopes which are now still being used for the medical purpose.
That's right.
Yes.
In fact, if I hadn't discovered plutonium and those transuranium elements, I'd be famous for discovering the medical isotopes.
In case of iodine-131, that is still being used. Iodine or iodine. In Japanese, we call it yoso.
Yes.
That is.
Iodine-131 is still used.
Yes.
Yes, absolutely.
And also, well, that saved your mother's life.
Yeah, actually, iodine-131 saved my mother's life. It's used in the diagnosis and the treatment of thyroid disorder, hyperthyroidism, and she was suffering from that. And she was very ill. And
the same disease killed your aunt or your mother's sister.
Yes, and the same hyperthyroidism had led to the death of my mother's sister. And she had a doctor who had taken some undergraduate research work with me at Berkeley.
Oh, really?
And he knew about this.
Yes.
And he sent her to a doctor in Hollywood who was just beginning to use iodine-131. And he diagnosed her as having this thyroid condition and then treated her, cured her, and she lived to a ripe old age, into her 80s.
You've been dealing with atoms and elements and nuclear things for so long.
I think my aim, my objective is just to increase knowledge.